Time scaling means if you want the signal to be in discrete time, we'll have it as stem everywhere so that will be relevant to our topic. So we will see stem everywhere. Only thing if you do in discrete, visualization will be somewhat difficult, but it's okay, that's fine. Time scaling means I'm going to compress or expand my waveform. I'm going to compress or expand my waveform. Okay, that is the meaning of time scaling. And this time scaling obeys the law of conservation of energy. So if you compress the signal in time domain, it will expand in frequency domain. If you expand the signal in time domain, it will get compressed in frequency domain because energy in time domain should be always equal to the energy in frequency domain. Or I can say the law of conservation of energy should be obeyed. So the energy which is the energy cannot be created nor destroyed. It can be transformed from one form to another, right? One form here is time domain. Another form is going to be frequency domain. So whichever domain you find the energy or power of a signal, it has to be same. So now time scaling, I write x scale equal to, I will copy the same thing because I'm using the same sine wave as example. I'm going to multiply this by a constant, and the constant is going to be 2. So it is x of at. So the entire sine wave inside the bracket is multiplied by a constant t. Now I'll be doing stem of t comma x scale. You'll see whether the signal is expanding or compressing. Able to see? This is the original sine wave, and this is going to be compressed sine wave. See here, I have only 5 cycles. I can see here completely in the first diagram. The second diagram, I can see 10 cycles. So which means I have compressed my sine wave. So the time period will be, here the time period is 1 millisecond for completing one full cycle, right? And here the time period will be 0.5 millisecond. It will be divided by 2. Whatever factor you are multiplying, it will be divided by